Thanks for having me. So today I'll be talking about our recent work on best possible one-time programs. So my name is Luowen, from Northeastern University, and this is joint work with Aparna, Jiahui, Justin, Bhaskar, and Mark. Yeah, and feel free to interrupt me with questions because um, I don't have enough slides for the whole time. So yeah, you shouldn't, but also don't feel obligated. But you should stop me when you have a question. Okay, so without further ado, let me start by introducing or recalling the definition of one-time programs. Okay, so one-time programs are originally introduced by the work of Goldwasser, Kalai, and Rothblum. And the goal of one-time program is to have a program that you can evaluate once and then self-destruct. So in particular, it allows you to choose some input X and then any input you want, and then it will give you the output of this function P of X for one time, and then it is supposed to self-destruct. And then when you want to evaluate on the second input X prime, you will not get anything useful out of it. That's the idea. Okay, so it shouldn't surprise anyone to realize that actually it is impossible to have a classical one-time program without any additional assumptions. So suppose your one-time program compiler, upon given some P, just output some classical bit string, like some obfuscated version of P, then you can always evaluate it multiple times by just making copies, right? So you can copy it once and then evaluate it on X1. And whatever happens to that copy, you don't really care because you have a second copy which you can subsequently do another evaluation with. So yeah, if your one-time compiler just output classical bit string, you can always copy it many times and you can evaluate as many times as you want. And because this is a quantum talk, you might probably anticipate that maybe no cloning principle will come to the rescue. So if you have no cloning, then it will mitigate this attack. Okay, but it turns out that this is by the work by Broadbent et al. 13 years ago, who also realized that even if you have no cloning or if you use quantum information to do one-time program, they are still impossible for a lot of functionalities. So in particular, suppose your P is a classical deterministic function, which is like the default scenario that we work in obfuscation. Then even if you use a quantum state for your one-time compiler output, it is still impossible due to the gentle measurement attack. So the idea is that suppose the one-time compiler outputs some quantum program, you can always do the following attack, which is that you query on some input, and then you measure the output to get the outcome. But because the P is deterministic, the output should give you the correct outcome with probability 1. And that means that the measurement here is actually gentle. So the quantum state is not really disturbed by this measurement. So everything in quantum is like reversible. So you can just uncompute and get back the original program, and then you can just query again. So even if you have a quantum program, you can still evaluate it on basically arbitrarily many times.
Excuse me.
Yes.
I have a small doubt here. This quantum program, it's a state, right? Is it not a oracle or something?
Sorry, what's the second part of it?
So here the quantum, here the program is encoded in a state.
Yes. Yeah, you can think of it as like a quantum advice that you feed into like a universal quantum circuit, and then it will give you like the universal quantum circuit will take this and also input xi, and then it will like just compute according to according to the circuit, and then give you the output.
Okay, so it's basically a circuit, not exactly a state.
Yeah, you can think of it as like a quantum description of the circuit. So it can be a classical description of the quantum circuit along with some additional quantum input at the beginning.
Yes.
That's another way to think of it. Yes.
Yeah, that's it. Thank you.
Okay. So, moving on. There is actually another attack that's like I don't think this is explicitly written down, but it's also not obvious. So the other attack is that if you have a one-time program, even if it's implemented by a quantum state or quantum device, not only you can compute it many times, you can also compute it coherently. By which I mean that suppose that you have some programs that cite P, you can always implement the following coherent map that maps X to X next to P of X. And the program state is not really disturbed too much by this process. Again, this is like, assuming P is deterministic. So the way you do this is pretty simple. Like suppose you have some superposition over X, you just coherently evaluate the program on this X, and then you just like do the same thing as the previous attack morally, which is that you are going to copy the output into a second register and then uncompute everything else. And what you are going to get in the end that you can show is that this will be close to like the original superposition over X along with P of X. And the quantum state that implements the program is not going to be decohered or entangled with this part of the output. So not only you can compute it many times, you can also compute over superposition of X coherently. So that's two attacks for.
Sorry, I have a dumb question. So why do you say approximately? Do you mean like if it's the computation is done with high probability, like it doesn't compute the function P with probability 1? Is that why you have an approximation?
Yeah. Or... Right. So if the program state computes the functionality with probability 1, then this is perfect. But if it's only close to 1, then this is approximate. Yes.
Right. Okay. Thanks.
Yes, thanks for the question. Okay. Okay. So subsequently, people realized that there is actually a way to get meaningful quantum one-time program. But to get this, you not only need a quantum state for your program, you also need to consider unconventional functionalities. In particular, the output of your functionality must be randomized instead of deterministic in order to get around the two attacks I just showed you. So by randomized output, I just mean that this is like some sampling functionality where on input X, this is going to sample some probability distribution that possibly depends on X, and then give you one sample of Y. So one example you can think of this is like the signing functionality of a signature scheme. So X could just be like some message, and D of X is just the distribution over the signature for that message X, and then you get one signature instead of the whole description of the signature distribution. So this is like one somewhat natural example where you might want to consider this scenario. And notice that once the output is pretty randomized, then the two attacks that I just showed you do not work, at least not immediately. So for the gentle measurement attack, well, recall that crucially for the attack to work, we have to say that the output must yield some particular outcome with probability close to 1. But if your the thing that you are measuring, which is the output, is actually very randomized and does not yield a particular outcome with high probability, then this is no longer a gentle measurement. So this attack doesn't appear to work. So if you uncompute, you don't know what you are going to get back. And similarly, for the coherent evaluation attack, if you try to do the same attack, again, in order to argue that you uncompute and then you get back the original program state, this relies on like the entanglement being very little, if not none, between the output register and the auxiliary register of the like by the auxiliary register, you can just think of it as like the program register, which is true if you are computing something that's deterministic, but it's no longer true once the output is potentially highly randomized. So yeah, so it turns out that you can get around the impossibility by considering both having a quantum program and considering a functionality whose output is randomized, but you need both. Okay, so this idea is possibly first realized by this work of Ben David and Sethas in 2019, where they proposed this primitive called signature token, which is exactly a one-time program for the signing functionality that I just mentioned. So again, the signing functionality is that you have some hard-coded secret key for the signing functionality, and then it takes as input some message, and then some additional randomness R is going, this is like a classical or maybe post-quantum signature scheme, and it outputs a signature. And yeah, and with the promise that the signature is going to be publicly verifiable. So anyone that has the verification key, which is public, can check that the signature is valid according to this message. And the signature token is just a quantum program that allows you to sign once. So the signing token is some quantum program that once you combine it with some message M, there is a procedure for you to produce one valid signature for M. And the security of the signature token says that if I just give you one signing token, then you should not be able to produce two pairs of message signatures such that, first of all, they are both valid signatures, so they both verify with the verification procedure. And second of all, they are for different messages. So this is the security notion that Ben David and Sethas are able to achieve with a quantum signing token. So it turns out that indeed there is something that appears that you can do with one-time program, at least for this special case of signing functionality for signature schemes.
So this is a one-shot signature, is it, or is it different from? What could you comment?
Yeah, this is a little bit. So first of all, one-shot signature is a different primitive that came after signature token. And second, the difference is that in a one-shot signature, the security should say that nobody can produce two valid signatures, even for the person. So like there is not a signing key. Like it just says nobody, even if you have the signing key, can produce two valid signatures. Here, there is a classical signing key, and if you have the classical signing key, you can produce as many signatures you want. But if you only have a token for the signing key, then you can only produce one signature. So that's the main difference. Yeah, so you can think of like one-shot signature as like somehow a public key version of this primitive, which is stronger.
Yeah. Right. Okay.
Yeah.
Thanks.
Yeah, but in terms of one-time program, we will not worry too much about one-shot signatures because, yeah, okay, well, I'll explain. Because at the end of the day,
one time.
yes. Sorry, go on.
Yeah. Sorry for the interruption. I was wondering if we had like the most general one-time program compiler, then would that also give us one-shot signatures? Is that immediate?
I think possibly with some strong assumption, but I haven't thought of that yet. But yeah, maybe I'll think about it offline and get back to you. It's an interesting question. Yeah, but I haven't thought about it yet.
Okay, thank you.
Yeah, but yeah, I guess what I want to say, like in terms of the perspective of one-time program, signature token and one-shot signature are both like a one-time program for the signing functionality. And I guess for this talk, I'm actually interested in extending this in the other direction. Okay, so let me explain. So yeah, so first let me tell you a little bit about what we already know about doing quantum one-time programs for randomized functionality. So as I said, the first work that I'm aware of is this work who did signature tokens. But what I'm interested in is whether we can extend it to other functionalities beyond signing. So last year, there are two works. One work is by Gan and Movasak, who actually look into this exact question, and then they constructed a one-time compiler for functionality. So it takes that input some randomness R and then some X, and then it outputs some output that has high mean entropy. However, the construction that they get, like the security that they prove for their construction, is actually pretty weak. So in particular, if you look at the security, like my interpretation of their security notion is that they really just mitigated a class of attack that morally captures gentle measurement, and like maybe a little bit more, but not too much beyond that class. So yeah, if you ask
are we
me,
looking for? I'm sorry.
yeah.
Didn't mean to interrupt, but now that I have, I might as well ask the questions. I was wondering, so we use a simulation notion of security here, or I guess you'll introduce it later, what notion of security we want from the one-time program.
Thinking about our work or their work?
Yeah, I was just asking what the accepted definition should be, like what a reasonable definition should be.
Oh, okay.
But I guess
That's an
you'll explain
excellent
it.
question. We'll get there.
Okay, sorry, yeah.
Yeah. Hold on, that thought, we'll get there very soon. Yeah, so yeah, so obviously the question going back, the issue with this definition is that it's like pretty weak, and it's unclear if this is the security notion that we are happy with. So there is a concurrent work with a subset of my co-author and Vinod, who also look at the same class of the most general classical randomized sampling functionalities. And the security they achieve is what we call a CSEQ security, which is a type of simulation security. But we'll talk about this a little bit more later. But the security notion that they propose here, which we call CSEQ, is really complicated. And it is unclear like what's actually being achieved of this simulation security. In addition, they also have some other results. So they also look at more specialized functionality like a PRF or a NISIC proving functionality. And the security, like what they show is that their compiler for these specialized classes also achieve specialized security notions. So for PRF, they can do like morally two-time indistinguishability, and for NISIC, you can do something like you cannot prove two NISIC statements. So I guess they did this in order to show that their compiler or their security is somehow useful, but still, this is still just the like the security notion catered to each application. And while you can say that they are probably meaningful security notions, these are still specialized security notions. Okay, and on the negative result from their work also consider proving an impossibility. So in particular, they consider some randomized functionality P who has high entropy, but is contrived. And what they show is that even for this kind of functionality, there is some contrived example where you cannot get the ideal one-time security. So where like the ideal security will just say I get one query X and then I get one sample Y. So this is impossible even if you have high entropy.
Sorry, so is it high min entropy or is it just high entropy? Because
yeah, it's technically it's high min entropy, but if you have high min entropy, it's also high entropy. So yeah, the difference doesn't matter too much, but like you should just the takeaway should just be that like just having high entropy or high min entropy on the output doesn't really save you generically from all impossibility results. Yeah, and for simplicity, throughout this talk, we will just consider classical ideal obfuscation or classical oracles as assumption and not worry too much about the concrete assumption being used here because we are interested in the general possibility of one-time programs, not what assumption you need to achieve them. Okay. Yeah, so with this prior work, it gives us a very natural question, which is that, so again, let's recap the situation. We have some ideal security notion where we say, okay, one-time program should just give me one query access to this functionality, but there are lots of negative examples where this is impossible in general. And then depends on different functionality. There are a bunch of different security notions that has been proposed and have constructions for. But if you stare at them for a little bit, it is clear that there is a gap between the security notion that's already being proposed and the strongest security notion that's being rolled out. So there's a big gap in the middle. So a natural question is, can we improve the security achieved in existing constructions? Or in the other direction, can we actually prove better impossibility to like push down the upper bound? So can we make them converge? So like, for example, maybe a very natural attempt at formalizing a security notion is called like two query security. Maybe you cannot come up with two input-output pairs that are both valid for some notion of valid, right? So, and for a lot of functionality, it's unclear whether we can achieve this two query security. So it would be really nice if we can understand this better and close the gap. So that's the central question that we will investigate today. Okay, so now let me move away from one-time program a little bit and then think about the many-time situation. So for many-time, there is an analogy called obfuscation. So in obfuscation, you are essentially doing the same thing. Like you want to protect the program, but instead of having the program being evaluable for one time, it can be evaluated for as many times as possible. And it turns out that, okay, first of all, this setting is actually a lot more studied. Like there are lots and lots of more papers studying this setting rather than one-time setting. But more importantly, actually for obfuscation, there is not a gap, unlike the one-time situation that I showed you earlier. So in particular, similarly in obfuscation, there is like the most ideal security notion called virtual black box, short for VBB. And we know that there are a bunch of impossibility for VBB for contrived functionalities. So they are impossible in general. But on the other hand, there is also this notion in obfuscation called indistinguishability obfuscation, or IO for short. And here, it turns out that there is not a gap between IO and VBB. So why is this true? This brings me to the work by Goldwasser and Rothblum in 2007, where they proposed this.
Can I ask a question before you explain the result about the curve? It's a very simple question, so maybe it's obvious. I thought I'd just ask. Suppose we just have a classical functionality, right, that we want to obfuscate, or a classical circuit we want to obfuscate. Does the curve change? This curve that you've drawn, right, between ideal VBB obfuscation and IO? No, in the next one, yeah. Does this curve change if you allow quantum? Or is the curve exactly the same?
I think it should be the same, but it needs to be double checked. Yeah, I think like the proof for the classical setting should also go through in the quantum setting. I think there is a paper on that.
I see. Okay, thank you.
Yeah, I think Sam Gang. If I remember correctly, Sam Gang had a paper about that for quantum obfuscation. Or maybe that's still classical functionality. I'm not entirely sure. Okay, but for now, let's just focus on classical here. Okay, so in the classical setting, yeah, there's this notion called best possible obfuscation. And this work not only proposed this notion of best possible obfuscation, they in fact prove that best possible obfuscation is equivalent to IO. So the interpretation of this result is that it bridges the gap between VBB and IO. So again, VBB is this really ideal security that we would really like to get for obfuscation, but impossible in general. And IO, for those of you that are unaware, is like a very general security notion. But in fact, when it was first proposed, people are really unsure what to think of it, because like the security notion a priori is not very clear how you can use it for application. Like it's only in the last 15 years or so where people start to understand how to use IO to do meaningful things. And best possible obfuscation, like this result that established the equivalence between best possible obfuscation and IO, says that actually you don't need to worry about what the security notion of IO means, because IO is best possible obfuscation. And what that means is that if a certain functionality can be VBB obfuscated, then IO, which is equivalent to best possible obfuscation, will achieve VBB for you. So that's just the idea of best possible obfuscation. If the functionality can achieve any security notion, then best possible obfuscation and thus IO will also achieve that security notion. So what this means for cryptographers is that rather than like focusing on every functionality and then think about what kind of security notion we can construct for each functionality, instead we can just focus on this general primitive called IO. And as long as we can construct IO, then we can get any security notion that is possible. So this is a really wonderful result. Yeah, and the question.
I'm a little bit sorry. Before you go on, just a small clarification. The best possible obfuscation, that is not a formal definition as such, is it? Like, because IO has like some formal definition of what it means to be, know, indistinguishable.
Yeah.
But best possible obfuscation is like English words, right? Like in the sense that it's saying that.
Yeah. So So in their paper, there is a formal definition of best possible obfuscation. For the purpose of this talk, like the precise definition doesn't matter too much. Like you can just think of the definition of best possible just mean, like for this talk, it just means if it can be VBB, if it's possible to achieve VBB, then your obfuscator should achieve VBB. But there is like a more well-defined notion for best possible obfuscation, but it's not important for this.
And how should I think about the case where you cannot realize VBB? what does it do in those instances? What does the security notion say informally in that setting?
Okay, so now let me give maybe the best way to answer this question is to actually give you the formal definition of best possible obfuscation. So
if you
in
want
their
to,
paper,
we can discuss it later. I mean, I don't want to interrupt. I'm sorry. We can discuss it afterwards if you think that's better.
no, it's fine. So yeah, so the way that they define best possible obfuscation, the idea is that best possible obfuscation, if I give you a best possible obfuscation, the view that you get from querying this best or having this best possible obfuscation should be indistinguishable from like some simulator who get any other obfuscation of the same circuit. So morally, like if some other obfuscator can achieve some functionality, then best possible will also achieve it because like by the simulation property, you can simulate their view just having the other obfuscator's output. Yeah, but for the purpose of this,
I'll ask for them. Okay, thanks.
Yeah, for the purpose of this talk, you can just think of like, if you can achieve the strongest BBB, then your obfuscator should also achieve it. For the simplicity of this talk. Okay, so yeah, so this is the reason why for obfuscation there is not a gap between like the security notion of IO and the most ideal security notion called BBB. So the natural question we'd like to raise in our work is whether we can translate this success story into one-time programs. So can quantum one-time programs also have the same best possible story? So maybe there is a generic one-time compiler or a generic one-time obfuscation security notion that achieves the ideal one-time security whenever it is possible. If this is true, then that would be really good because instead of focusing on different, like 1,000 different one-time security notion for each application scenario, we can also, like for IO, just focusing on achieving a single security notion. Yeah, so the concrete question here is whether it is possible that there is a generic one-time compiler that achieves the best possible security, one-time security for any functionality. Okay, so far I've introduced the background for one-time compiler and the motivation for studying best possible one-time program. So now I'm actually going to introduce our results. So the results will be twofold. So the first part of the result, I'll actually show you why best possible one-time programs are impossible, unlike many-time obfuscation. And I will show you a proof sketch for why this is true. And for the second half of our results, I'm also going to discuss how we can get around the impossibility. So in doing so, we'll propose some new one-time security notions. And we'll also generalize our discussion of one-time program from not just classical randomized functionality, but also quantum functionalities. And we'll also discuss our new constructions of one-time programs and how they achieve these new one-time security notions. And why they are also related to best possible one-time programs, even though like we are not going to achieve the thing that we rule out in the impossibility. Okay, so moving on, let me just show you our first result, which rules out best possible one-time programs. Okay, so formally.
Sorry, but are you going to give a formal definition of best possible one-time program later, or?
Yeah, I intentionally are not going to give you the definition, but I think it will be clear. Like, I think the proof is clearer than the precise definition, because
okay. Okay, sounds good. Thanks.
yeah, because like we can debate about the definition, but the proof, I think, is the less debatable part. Yeah, but for now, just think of best possible one-time compiler as like achieving the most, like you can just think of like it achieves the ideal one-time security if it's possible. So that's the object that we are ruling out here. Okay, so our formal result is that assume that there is lossy encryption, then you cannot have a generic best possible one-time compiler. Okay, and lossy encryption is a cryptographic primitive that we know how to construct from somewhat standard post-quantum assumptions, such as learning with errors or weak pseudo-random group actions. And furthermore, this is true relative to any oracle, including the standard model.
So how should I think about lossy encryption? Sorry for the interruption. Is it like it just leaks some of the ciphertext? Oh, sorry, some of the plain text? Is that how I should think about it?
Okay, for now, you can just think of it as some public key encryption scheme that satisfies an additional property called lossy, like lossy security. But yeah, I like in the proof, I'll show you like what it does. Don't worry too much about like for now, just think of it as a cryptographic primitive.
A small doubt. When you say generic, like there are no generic best possible one-time compiler. What does it mean? Is it like for you're trying to give for every family of functions, or
Yeah. So by generic, I mean that there is one single compiler that achieves best possible security, just like I/O. Like I/O, there is a single construction of I/O. Well, maybe there are different padding lengths, but it's a single construction that achieves the best possible obfuscation in the classical case. And here, this is the same thing that we are trying to match. So we are not ruling out that like for every functionality, there is some way of achieving like the best possible security notion. Once you cater your compiler to the specific functionality, that's not what we are ruling out. We are ruling out a single compiler that achieves every best possible security, which is what you get classically for many-time obfuscation.
Yeah, thanks.
Yeah, thanks for the question.
But can we come up with some notion of like, can we draw a line where for the family of functions for which we can achieve this best possible OTP compiler, or like can we draw
Yeah,
a strict line?
We'll get there. Yes.
Okay.
Yeah, but for now, we're focusing on the completely unrestricted case. So we are considering every possible functionality, and we are going to match the security notion we achieve with every possible one-time compiler. Yeah, but we'll discuss this more later. Okay, so now let me tell you a little bit about the proof. So actually, if you know the formal definition of lossy encryption, and you know that this is the theorem that you are supposed to be proving, then the proof is not too hard. Like you can probably figure out if you stare at it for long enough. So maybe instead, let me tell you how you might even realize that come to realization that you might want to look at lossy encryption in the first place. Okay, so suppose we are just trying to investigate best possible one-time program. What do you do? Well, here's a very interesting functionality that you might consider. So consider the following functionality, D, where the functionality upon input X is actually going to ignore X and then just sample from a fixed distribution and then output that sample. Okay, so my claim here is that for this somewhat contrived functionality, there is actually a one-time compiler that achieves the ideal one-time security. So how do you do it? Well, when I'm given some D as my input, and I am a one-time compiler, I am just going to evaluate D on some fixed input, let's say 0. And I get one sample, right? So I'm just going to output a constant program that whatever input I get, I just output Y. So so first of all, this is one-time correct because no matter what input you give me, I'm supposed to sample from C, and the output of this program indeed is a sample from this D0, which is C. And on the other hand, this also achieves one-time security, like the most ideal, the strongest one-time security that you can come up with, because the entire program description of my output, you can simulate by just having one classical query to D, right? Because you can simulate this by just querying D on 0, and then you output the same constant program. So for this class of functionality, you can only you can actually achieve the strongest ideal simulation security. However, notice that for this construction to work, it is crucial that the functionality class that I'm considering is a constant distribution functionality, by which I mean like it outputs the same distribution for every X. And notice that for this to work, like the functionality doesn't have to ignore X, right? It can maybe use some X, like it can use the input X in some maybe obfuscated way, but as long as at the end, the output doesn't actually depend on X, then this construction will work. So the insight here is that, well, if a program is trying to hide from you whether it is actually using the input or not, and it is like a randomized output, then you should not be able to really distinguish whether this program is always outputting the same distribution for every input or not. And this is where we use crypto to formalize this unlearnability or untestability, efficient untestability notion. Okay, so here's how we a little bit more formally write down how you do this impossibility. Okay, so suppose there is a generic best possible one-time compiler OTP star, and again for now let's just think of like it should achieve the ideal one-time security when it's possible for the functionality. Otherwise, I don't really care. Okay, so from lossy encryption, we can construct two classes of functionality. The first class of functionality D is just going to output the same distribution or output one sample from a certain fixed distribution that's independent of X. So this is like a constant distribution functionality, exactly that the one that we described in the slide in the previous slide. And the second class of functionality is we call E. And this class of functionality is going to be injective on X. So the output can always be inefficiently or efficiently inverted to X. So for those of you that know what a lossy encryption is, like D is just going to be the encryption algorithm with a lossy public key hard-coded, and E is going to be the encryption algorithm with like the injective mode public key encoded. And what the guarantee that you can get from lossy encryption is that the circuit family D is computationally indistinguishable from E. Yeah, and this construction is like pretty straightforward if you know what the lossy encryption is. But this is the property that we will need to use from lossy encryption. Okay, so now for our proof, let's consider what happens if we just apply the supposed best possible OTP star to both D and E without knowing which is which. Okay, and I claim that the following must happen. First of all, if D is fed into OTP star, then by best possible security, it must be the case that OTP star of D is going to look like a constant program. So this program outputs the same thing for every single input, which is stronger than X, like the original D that outputs one sample from, but drawn from the same distribution, right? Because if you just feed it X or a different X, every time you might get a different output. But for a function program, you can evaluate on every X, it's going to give you the same sample every time. So that's the claim. And what happens if we feed E to OTP star? Well, I claim that what must happen is that by one-time correctness, OTP star of E should still retain the input-output dependence. So what this means is that it must not be a constant program. So again, by one-time correctness, OTP star of E, when you give it X, it must be injected from X. So it cannot be a constant program. And now we have a contradiction because we can always efficiently test whether a program is constant or not. So we can distinguish OTP star of D and OTP star of E. So from this, the conclusion is that the OTP star procedure must be inefficient in order for this to happen, because otherwise we have an efficient distinguisher that breaks lossy encryption. Okay, any question before I move on?
Okay, so this sort of makes sense. So, thank you. Yeah, you were right. I think it's much easier to understand without going into the formal definition. Just looking at this, I just had a small silly question, which was, so why did people start considering lossy encryption in the first place? So I'm guessing lossy encryption is somehow the notion that I quickly looked it up. So it looks like it's a notion where you're losing some information about the inputs. It's not necessarily injective after the encryption.
I mean, I know like lossy encryption is like very old, 20 years at this point, and definitely people didn't propose this notion to rule out best possible one-time programs. Yeah, I think, yeah, they have various applications before this work, but I don't know what the original motivation for this was. Yeah, but they are cryptographically useful.
But how did you know about them then? Like, because like I never encountered them, so that's I'm a bit curious. And like, what context did you stumble upon them?
How did I know this, or are you asking how did I know this, or how did a cryptographic community know this?
Well, I would be interested in both, but I was asking you personally, like, how did you know that this thing exists if you don't know what the application is?
Okay, yeah. So I guess I came across this because I was proposing this, basically this exact proof sketch to one of my co-author, Mark. And Mark said, well, I don't know if it's Mark, but probably one of my co-authors said that, well, you can construct this from lossy encryption.
I see. Okay. Awesome.
Yeah.
Okay, thank you.
And I guess for the general community, I think I'm not entirely sure, but people initially realized they can do this from, I forgot, factoring or LWE, and then eventually we came up with application for it. But it's kind of, yeah, I don't know the literature well enough to tell you how people came across it initially.
if it's sorry for the distracted.
No.
One small follow-up, which was this. Do we know of post-quantum lossy encryption schemes as well?
Yeah. So
okay.
I explained earlier that you can construct them from LWE and pseudo-random group action, and both of them are supposedly post-quantum, at least post-quantum for now.
Okay. Thank you.
Yeah, and the reduction is post-quantum too. So
yeah, that's the part I wanted to check. Okay, go.
Yes.
Thanks.
So in our paper we do give like a complete construction reduction. So you can read that if you are interested. Okay. So I guess I glossed over this little detail, which is why OTP star of D must be a constant program. So that's the part I am going to explain next. So why this must be true? Okay, so here's the argument. If you have a constant distribution sampler D, well, here's a fact about it. It is actually one-time equivalent to a mixture of constant function. So again, the constant function is just you hard code y, and whatever input x and randomness you are given, you just output y. And y, so D is going to be equivalent for this mixture for a y drawn from D. Okay, so why is this a useful fact? Well, best possible security says that because D is one-time equivalent to the following one-time implementation mixture of C of Y, like whatever you can learn from a mixture of C of Y, like you can morally, like that's the most amount of information you can learn from OTP star. So the definition, formal definition of OTP star says that because this is ideal one-time access simulatable, then OTP star should also satisfy ideal one-time security, which means that this should also be simulatable from just having one sample of C sub Y. But if you think of it, this is kind of ridiculous, because if you only have one sample of C sub Y, then what can you do with it? Like this is just a constant program, right? So by correctness of the simulation, you must also output a constant program. So putting everything together, we conclude that OTP star of D must also be a constant program. Okay, so far I actually maybe let me pause a little bit for questions. Okay, so that basically concludes the negative results in our work. And now I'd like to discuss how you can get around this impossibility. So as I already alluded to earlier, there are two approaches that you can take to get around the impossibility. The first approach is that rather than considering the class of all possible efficient randomized functionality or quantum functionality, you are going to just look at some subclass of protected functionality that is not ruled out by our impossibility. However, I think for the rest of the talk, I want to actually focus on the other approach, which is that rather than considering all possible one-time compilers, all efficient one-time compilers, we can maybe achieve something when we only restrict to considering a subclass of one-time compilers. Okay, so how might we want to do this? Well, notice that our impossibility, the proof of the impossibility, as well as the definition of best possible obfuscation, even though I didn't actually tell you the definition, there is one crucial thing that both of these rely on, which is that we are comparing our supposed best possible OTP star with any possible implementation of one-time correct implementation of the same functionality. And in particular, this includes what we call a mixed implementation. So So your implementation of this quantum circuit or this randomized functionality can be a mixed quantum state. Like it's a mixture of a pure state. And crucially, we allow your implementation to be one-time correct only after you average over the mixed state. So averaging over the piece of ice here. Okay. And maybe you can ask this somewhat natural question, which is that can we get around the impossibilities by considering, like, instead of every possible efficient implementation, what if we just focus on one-time compilers that morally only output pure program implementations rather than mixed implementations? Can we get around the impossibility that way?
Sorry, can I quickly ask a question?
Yeah.
So I think I missed like the beginning, but like the impossibility result that you were showing like applies for like both classical and quantum OTP, right? Like there was like nothing quantum in the example you were using.
Yeah.
Like
so the impossibility. Yes. So the impossibility is for all randomized functionality. So this it rules out all classical randomized functionality, and randomized functionality is a subclass of quantum functionality. So it also rules out for like the more general class of quantum functionality. Yes.
Okay, good. And the second part of the question, like, how does this impossibility compare with like the construction, let's say, from like one-time memories or like this other, like even like the classical constructions for like one-time programs? Like, where is the part that sorry, I think I maybe missed at the beginning, so maybe you were already
Yeah. No worries. So so as far as I'm concerned, one-time memory and the classical one-time program literature consider like they have some hardware assumptions. So either you have some like classical hardware that that's a black box that's a black box for security purposes, or like there are also some works that consider like the NISC scenario where like there is some capability restriction on the adversary. Yeah, so and in this work we consider like everyone is fully quantum, like fully fault tolerant, and no hardware assumption. That's the setting that our work focuses on.
Right, but does your impossibility result, for instance, also imply that it's impossible to like realize these functionalities? Because you have like a strong impossibility result that in principle to me it should even capture like this other assumption, like these hardware assumptions. Does this say something implicitly about those? Like, I don't know.
That's a good question. My intuition is no. Okay.
Because here in this impossibility, you were just saying, okay, I have like this black box thing that achieves this functionality. It doesn't matter how we implement it; it's impossible. So to me, it also sounds as if it should rule out any kind of like construction, even from like some crazy
Yes. Okay. Yes. Okay. So the answer is no, and the reason that it is no is because of the part of the impossibility proof that I didn't tell you, which is this part. Like I claim that there is an efficient test that distinguishes a constant program from non-constant program using one single query. And that is the part that breaks down when you have hardware assumption or like NISC. Because here, what you do in the efficient test is actually use like a superposition query to test whether the output is constant or not. So this is the part that will break down when you have hardware assumption or NISC assumptions.
So maybe I don't have like the right intuition. So what is this efficient text in the context of OTP?
Right. Okay. So this is our like the high level idea of our impossibility. Like we have some. We started with some computationally indistinguishable class of family, And then in the end, we came up with an efficient test because
this is something that you came up with. Okay, I see. So like something.
Yeah, this is the contradiction. There is some transformation that we can distinguish. Like if OTP star is correct, then on one hand, this is a constant program. On the other hand, this is not a constant program. And this is the part that will break down if you have Harvard assumption or NISC assumption.
I see.
Yes.
That's great. Thank you a lot.
Can I ask a follow-up question? Now I got a bit curious. You said that to do the efficiency test, to do the test efficiently, right, to distinguish the two cases, you are saying somehow that you have to make a superposition query. But does that mean that if you are classical, you couldn't construct an efficient test? That's a bit
classically
odd,
you can do this too, because classically you can just rewind.
Oh, I see. Yeah, then you can run it many times anyway.
You can
rewind. Got it.
Yeah, for quantum program, you do superposition query.
I see.
If you have Harvard assumption or NISC assumption, then I don't know how to do it.
Right. Obviously, you shouldn't be able to do it, right? Because there are.
Yeah, you shouldn't be able to do it. Exactly.
Okay.
Exactly.
Okay, fantastic. Thank you.
Okay, yeah. Thanks for the excellent question. Where were we? Oh, okay. Yeah.
I think here.
Yeah, we were here. Yes. Okay. Yeah, trying to rewind to the previous state. Okay, yeah. So yeah, our impossibility crucially relied on like comparing our one-time program compiler with a mixed implementation of the functionality. Yeah, so the idea is, can we get around it by only considering one-time compiler that output pure program? Okay, so it turns out that you need to be very careful to define what it means for a one-time program to output pure state. Because if you just do it naively, like I only look at the every pure state in the support and then say it must be like a one-time program, you don't really get around the impossibility. So recall that the like the bad counterexample or like the bad one-time implementation that we would like to rule out is just this mixed row over like constant program C sub y, right? This is the thing that we would like to exclude from consideration in order to get around the impossibility. But there is a way that you can do the same counterexample with only pure states. So the idea is that we're going to consider some random phases R and consider the class of pure state family where you have basically superposition of square root py cy, and then you just add some random phases in front to like hide the fact that this is a superposition. So if you average over the random phases, then what you get back is exactly the same density matrix. However, notice that here, if you consider psi r to be the program that just like measure the cy in computational basis and then run it, then this is, on the one hand, it's a pure state, but on the other hand, it is still a valid one-time pure implementation for the thing, for the original constant distribution functionality. So if you just define pure one-time program to be like, it needs to be one-time correct for every pure state in the support, this doesn't really get around the impossibility. So you have to do define this in a more careful way. Okay, so that's where we arrive at this notion that we proposed called testable program, which is exactly this more careful definition of like a pure state program. So the idea is that rather than saying that we look at every pure state in the support, which is not really operationally well-defined and is not mathematically unique, rather we are going to consider a testable program to be two programs. So it is a pair of two programs. The first program is just the quantum program as before that implements the supposed functionality. And in addition, we are also going to have a second program that allows you to reflect around this pure state. So in other words, this reflection program allows you to test whether the first program is the supposed state. So what this buys us is that now, when I have some mixed state, the pure decomposition is not just given mathematically. It is given by this explicit program that that explicitly decomposes the mixed state into pure states. Yeah, so maybe a little bit more formally, a testable program is basically like a pair of two programs where the second program always gives you the reflection oracle for the first pure state. Yeah, and we can also define a testable one-time compiler. It's just a one-time compiler that outputs mixture over testable program, psi, r psi. And we also require that every psi in the support to be a pure one-time correct implementation of the original functionality. So hopefully this will get around the impossibility about it. Okay, but before I tell you that, maybe let me first highlight that it turns out that testability actually is a somewhat natural property of all existing one-time program constructions. So let's start with the easiest example. If your one-time program is just a classical program, then you can trivially augment it with a reflection oracle because you can always reflect around a computational basis state. And if you look at all the prior construction of one-time programs, they all follow the following template, which is that the output of the one-time compiler has two parts. The first part is just an unclonable token, usually a substate or subset state. And the second part is a classical obfuscation of a classical program that only collaborate with you for computing P when you measure the token in some random basis. So for this class of construction, which is essentially all prior construction, you can also make them testable because, well, for the first part, you can reflect around the token by just using the obfuscated program to help you test whether the token is correct. And the second part of the program is classical, which we already established is like trivial to do reflection. So for both of these, you can pretty easily augment the existing construction so that they are testable. And like this is like basically a black box construction that doesn't require you to know the secret randomness that you use to like produce the obfuscation or one-time program. On the other hand, the thing that we would like to rule out, which is the bad counterexample earlier, where we have a mixture of constant program, which is a valid implementation for a constant distribution. Well, this is intentionally excluded. Like we don't see how you can make this testable. In fact, it shouldn't be testable. Okay, so the takeaway is that the notion of testability that we described, on the one hand, it captures all existing one-time program constructions from the prior works. On the other hand, it also excludes the bad example that we would like to exclude. Okay, so now that we have laid the groundwork, I can now finally introduce you to the first positive result that we achieve in this work, which is that we actually give a best possible testable one-time compiler for all randomized functionalities. And this is relative to a classical oracle, which is morally the same assumption as the prior work. In fact, for the same assumption, we can even extend this to all quantum functionality. So basically, once you restrict the class of one-time compiler from every possible implementation to just pure or testable ones, then best possible security is indeed achievable. Okay, so next I'd like to talk a little bit about what it means for a one-time program for a function to have a one-time program for quantum functionality. So to do that, let me actually go back to the simulation security notion that I mentioned earlier. So there is this CSEQ notion, which stands for classical single effective query. So this is a one-time simulation security that was introduced in this prior work by some of my co-authors and Vinod. Okay, so let me tell you what it is now. So suppose we have some randomized functionality F, because their work consider randomized functionalities. The CSEQ security says that the view for any adversary querying the one-time program, well, this view should be simulatable by just querying a restricted CSEQ interface. So you don't get to query the full F, but you only get to query a restricted interface. And the idea of this interface is that this interface will allow you to do one single query to F, but if you want to do anything else, it's going to refuse to collaborate as much as possible. So for an example, you can always compute and uncompute immediately, because like the adversary has like a quantum program, so they can always compute and uncompute. But if the adversary decides to measure the output of the one-time program, then ideally this interface will stop working for subsequent queries. So that's the idea. And indeed, in this prior work that I mentioned, they construct CSEQ secure one-time programs for all randomized classical functionalities, and they do it in the classical Oracle model. Okay, so what is this CSEQ interface? Yes.
So maybe just understand at the high level. So are you kind of like saying that this construction that they were giving in this prior work is also good enough to satisfy your new definition of like the close to best possible, or you need to like still modify their construction to achieve that?
Okay, so to spoil what's going to come next, the answer is yes. CSEQ basically is best possible testable, but we'll get there.
Okay. Sorry, just want to like see at the high level if it's the same
Yes,
but in both works. Okay.
Yeah. Thanks for the question. Yeah, we'll get there, but yes, the answer is yes.
Okay, thank you.
Just to give you the takeaway. Okay, so going back, what I want to say here is, okay, so what is this CSEQ interface? Well, here's the formal definition. It's actually quite complicated. So I am not going to even try to explain to you what this does, because actually this is not complete, because it also uses compressed random oracles here. And I am not going to have the time to tell you what's a compressed random oracle. Instead, I'm just going to tell you our new definition, or the SEQ interface, which we generalize CSEQ to all quantum functionalities. And unlike the previous slide here, it's just 4 lines. Okay, so what's the general SEQ interface? Well, consider you have some quantum functionality psi, which is a channel, general quantum channel, anything, okay? And we are going to take a Stein spring dilation unitary, any efficient dilation, or like purification, U psi, which acts on the query register and some private purification register. And the private purification register is initially O0 without loss of generality. Okay, so the SEQ query interface acts on 3 registers. So again, it's going to act on the input-output register Q of the original channel and the private purification register of the dilation unitary. And there is also a 3rd register, a hidden counter register C, which is just a single qubit. So all of them are initially initialized to 0, except for the input-output, which the adversary, or like the user, gives. So it's going to implement the following map. So it maps any query with private register initialized to 0, well, this is going to map it to the dilation unitary applied to the input, and the counter being switched to 1. And this is like a self-adjoint map. So if you query it again on this state, it will send you back to the original state. And this has and this acts as in addition, this oracle acts as identity everywhere else. So and so this thing has an efficient quantum circuit implementation here. So yeah, it's like a 3-gate thing that you can very easily implement. So the idea is that you query it, you get the output, you query again, you get back the input. But if you try to do something in the middle, hopefully this interface is going to try to stop you from doing that. Okay, so maybe it will be helpful if we consider some example on what happens if we apply this interface on some channel. So in order to see why this might be a good one-time interface. Yes.
Sorry, just a small question. So is the oracle maintaining state essentially, in the sense that is the C register private to?
Yes. So so this is a stateful oracle where you can only see this register, and these are the private state of the register of the oracle. Yes. And this is also true for the prior CSEQ. It also has some private state.
I see. Okay. Thanks.
Yeah. Okay. So let me give you an example. So here's the example we like to consider. So consider the random querying channel phi n, where you give it some input. It's going to just ignore the input and then output some random coins uniformly at random. So n random coins. Okay, so we can consider the dilation unitary, one dilation unitary as follows. So so consider like it on some input Q, whatever state, and then the purification register has 2 0 register. What this unitary is just going to map this to an EPR pair on the output register and the one private register, and then it's going to hold the original input hostage in the private register. Yeah, so if you trace out the private register, this implements the original channel. But this is a unitary. Okay, so what happens if we apply the SEQ oracle onto this Dine-Spring unitary? Well, then it's going to implement the following unitary, which swaps the psi on input O0 everywhere else with the state EPR pair on Q and P sub R, psi in the original private psi from the original input in the now in the private register, and then the counter being incremented to 1. So this interface is going to swap between these two states and then access identity everywhere else. And again, like the adversary only, or like the user only gets to see the Q register and nothing else. Okay, so now let's see what happens if we try to use this interface as a user. So we start with some state that we would like to query to the interface, and PC, like the P register and the C register are initialized to 0, which we don't control. If we query this interface, then on the Q register, we'll get a uniformly random R as we intended, because this is supposed to give us one query access to the original channel. Okay, so if we don't measure this and then just immediately query it again, then by construction, this is like just going to map us back to the beginning. So we get back our original input state. Now, what happens if we actually, after one query, actually measure the output? Then what you can see is that this state is going to collapse from an EPR pair to just RR psi 1, right? And this state has like an inverse exponentially small overlap with this, with any thing, like with the substate that's spanned by EPR tensor identity tensor 1. What that means is that if you query it again, there's like an inverse exponentially small amplitude that's being mapped back. and everywhere else is just going to be act as identity. So essentially, this is like you can interpret this as like with all but inverse exponentially small probability, this does nothing. So it rejects your query. Level idea is that this indeed gives you like the ideal one-time access that you would like for this channel. But this works for any channel, not just this random querying channel, which still has a classical output. Okay, so
sorry, I have one quick question. So isn't a sort of like if I had the ability to keep state, right? I could just keep track of whether you've asked me a query or not, and simply refuse to answer if you make this the next query, right? Like I just keep a counter.
Yeah.
And
good.
Is that
good.
not a good definition? Like, so what's the distinction? Could you comment a bit on this? I think I'm getting a bit lost.
Oh, that's a great point. So the difference between your interface and my interface is that my interface is unitary, whereas your interface, yeah, it can be made a unitary, but I guess the more crucial point here is that I can also give you the inverse access to this unitary. So in your example, that wouldn't help because the adversary can always uncompute. But here, give the ability to uncompute doesn't help. Well, first of all SEQ is like self-adjoint. So I don't even need to give you inverse. You can just like compute it yourself. And so I guess the most important point is that here, giving you inverse access still doesn't allow you to get around the one-time interface. Whereas the naive counter will, like you can like query the inverse and then you can query again, which is what we want to avoid.
Right, got it. Thank you.
Yeah, so that's why we like want to have like a self-adjoint unitary, so that like because we cannot stop the adversary from uncomputing, so we would like that to also leak as little information as possible. Okay, so why do I spend so much time to tell you about SEQ? Well, the next contribution of our work actually says that SEQ subsumes CSEQ. So rather than worrying about that super huge definition, now you can just work with this cleaner definition of SEQ. So in particular, formally we showed that for every non-trivial randomized classical functionality F, by non-trivial, I just mean that like you can query F on more than one different input. You can query it on at least two different inputs. Then there is always a channel wrapper phi sub F, such that you can intersimulate between OCSEQ of F and OSEQ of phi of F. So the takeaway is that SEQ, what this means is that SEQ is actually a generalization of CSEQ. And at the same time, it also like much simplifies the CSEQ definition. In particular, you can just understand the CSEQ definition achieving prior work. It's just this more simpler SEQ using a particular quantum channel wrapper for the classical randomized functionality F. So I'm not really going to tell you the proof because, well, CSEQ is complicated, and as a consequence, the proof is also complicated. Okay, but I guess the more interesting here is the following result, where we show that actually SEQ security actually gives you best possible testable one-time programs. So formally, we show that if you have a one-time compiler that achieves SEQ security, it is best possible. It also achieves best possible security amongst all testable one-time compilers. So the takeaway here is that SEQ actually plays a very similar role for testable one-time programs. Notice that it's testable, not all one-time program, as the role that VBB plays for obfuscation. So the reason is that SEQ is a simulation security notion. So you can think of SEQ as the BBB analog for testable one-time programs. Yeah, and moreover, like this implication also relativizes for all oracles. Okay, so once you have this stronger theorem, actually in our paper, we prove a stronger theorem than the original theorem 2 that I told you about, which is that we actually construct SEQ secure one-time compiler for every quantum functionalities in the classical oracle model. And this allows you to recover the original theorem 2, because once you combine this new theorem with the theorem from the last slide, you get the original theorem 2. So in particular, this theorem says that you can get SEQ security, and the previous slide says SEQ security implies best possible testable one-time program. So yeah, so in the end, you get best possible testable one-time program in the classical oracle model.
So when you say the classical oracle model, does that, like, is it like the random oracle that is used to instantiate?
Like,
how should I think about it?
No, yeah, good question. You should think of it as like ideal classical obfuscation.
So if you have like VBB, then you can do it something like this,
so
and then VBB you instantiate with IO instead. Okay.
Yeah, so post-quantum VBB for classical functions, you get this.
Got it. Thank you.
Okay, so with the remaining time, let me quickly tell you how the construction of SEQ secure one-time program works. So actually, the idea is pretty straightforward. Once we've established all this groundwork like SEQ, yeah, because like here's a very natural idea. Like in order to get SEQ security, if we can just obfuscate the SEQ interface, then we'd be done. Because again, the security just says it should be simulatable from SEQ interface. So if you obfuscate it, you start with functionality, you wrap it in this SEQ interface, which is efficient. If you obfuscate it, then you will be done. Now, as Atul already mentioned, like there is a catch, which is that SEQ is not really a traditional interface that you have. It's a stateful oracle. What that means is that SEQ not only takes a public query QI and then outputs some output QI plus 1, it also maintains some private state SI. And once you query it, it's going to update the private state for the, and this state is going to persist across calls. So this is not a traditional interface where you have a classical function, stateless function, or a stateless unitary. So in order to obfuscate it, we must be able to handle stateful and hide the state in some way. Okay, so in our work, we address this by proposing a new primitive called stateful quantum IO. So the idea is that rather than the traditional IO definition, which considers stateless programs, here we consider a stateful program where this quantum program can have some initial private state, as well as a evaluation unitary U, and the stateful quantum IO is going to output an obfuscated stateful program, util, and the obfuscated state. And the guarantee is that if I have two pairs of U psi where the behavior of them are indistinguishable for every polynomial sequence of calls, then the obfuscation you get out of this stateful quantum IO should also be indistinguishable. So that's the guarantee. And we don't construct this. Instead, we construct something weaker, which is state well, not weaker, but like incomparable. We consider ideal stateful obfuscation. So in particular, we assume ideal obfuscation for classical function, we construct ideal stateful obfuscation for stateful quantum functions. So the idea is pretty simple. Suppose you start with some stateful program, if you have ideal obfuscation, I can just use a quantum authentication scheme to authenticate the state, which also encrypts it. And the output is just the authenticated state along with the obfuscation of the original unitary. And to evaluate it, I just give you this obfuscated unitary, which basically just like decrypt the state and then runs the original unitary and then re-encrypt it. So like a very common obfuscation recipe. And so this you can instantiate with just ideal unitary obfuscation. And you can instantiate ideal unitary obfuscation with ideal classical obfuscation using this prior work by Huang and Tang. And yeah, in our paper, we actually showed that if you start with like I/O, you should also be able to get stateful quantum I/O, and that also suffices to get best possible one-time program. But we don't know how to construct quantum stateful I/O, but we believe that this recipe should still work. It's just that the security proof runs into some subtle issue that we don't know how to handle with standard model I/O. Okay, so I guess with that, I am going to wrap up. Okay, so yeah, so that brings me back to the graph that I showed at the beginning of the talk. So in our work, I guess we basically push up the existing security notion achieved from all of these ad hoc security notion and CSEQ to best possible testable one-time program, which we know how to construct, at least with a classical oracle. On the other hand, we also identified this notion of best possible one-time program, which is the unrestricted notion. And we show that you cannot achieve this line, at least not generically, for every functionality. And there is this counterexample called constant distribution functionality, which you can achieve not generically, but you can achieve it if you know the functionality is a constant distribution. So this still leaves a gap between best possible one-time program and best possible testable one-time program. So these two lines, which is untestable one-time program. So so a natural question, which is a question that I find fascinating, which is, can you come up with untestable one-time compilers? Well, beyond this somewhat useless counterexample. And maybe to further motivate the study of untestable one-time program, in our paper, we also have like a small side result where we show that you can carry out a generic multi-observable, multi-input attack against all testable one-time program. And this attack doesn't seem to work on untestable one-time program. So it seems that there is still something to do beyond testable one-time program. Yeah, so that's the end of the talk, and I'll take questions. Thank you very much.